Alright, so in this section we're going to talk about the Euclidean form and the Gauss-Jordan elimination method. So first of all, what is Euclidean form? So Euclidean form is any matrix that follows these three criteria. So it's an n by n matrix B is a Euclidean form if all three are applied. All rows that consist entirely of zeros are grouped together at the bottom of the matrix. In every non-zero row, the first non-zero entry from left to right is a 1. And last one is if the ith plus 1 row contains non-zero entries, then the first non-zero entry is in the column to the right of the first non-zero entry in the ith row. This one's going to be a little interesting. It's very theoretical, mind you, but I'll give you examples of what they really represent. And the last little note down here is every matrix that is in Euclidean form is in reduced form. That's a key thing. So basically, our method is we want this at the end, right? If you wanted a 3 by 3, this is in reduced form or Euclidean form. No hint for right now. Provided that the first non-zero entry in the row is only non-zero entries in its columns. Okay, so basically like the diagonals. Okay, so what does this really mean? So number one is pretty straightforward. It's basically our goal when it comes to solving for linear equations. So this is called an Euclidean form. Okay. Another one, oh sorry, this is number 2, sorry. This is the second part, this is number 1. So when we talk about the zeros at the bottom, we have something like this. Okay. That's what number 1 says. So all rows consist entirely of zeros are grouped at the bottom. So they're grouped all at the bottom. In every non-zero row, the first entry is a 1. First entry is a 1 in the rows. And then the third one kind of looks like this. This is kind of an extreme example. Now, the reason why this is interesting, this is where the third one talks about. If the ith plus 1 row contains non-zero entries, so these two here represent non-zero entries, then the first non-zero entry in the column to the right of the non-zeros is the ith row. Now notice we have this one. Now what's to the right of it? A 1. So that is what number 3 represents. Okay, it's a very obscure one, but it's basically saying this is completely already reduced. So not only do we have zeros on the bottom, but we also have zeros in the column as well. Okay, so this is completely reduced, even though it looks kind of funky. This is what they mean by the third entry there. Okay, so let's see an example of how this is going to work and how these are applied to solving for a system of equations. So we want to solve for this system here. Okay. Now, this is actually already. Now, let's see what we have here. According to our rules, right, we want it in reduced form or row echelon form. So we have the first entry being 1s. And now this rule applies number 3, right? It's our price. The next one to the right of it on the next row is complete there. So if it's already reduced, what's the answers, right? Because this was our goal, and then these will be the answers themselves, B1, B2, B3. But this case, what's our really answers? So at this point, we had no choice but to go backwards. Meaning, how do we augment this matrix, right? So what we're going to do is, well, now we have 1, 2, 3, 4, and this is considered our answers here. This is our B's. So we have x1, x2, x3, and x4. So we have 4 different variables, and these are my answer choices. So we have x1 plus 2x3 is equal to 6. We have x2 plus 3x3 is equal to 5. And then we have x4 is equal to 4. So we found one complete answer here. So what we're going to do is we're going to solve for x1 and x2 and have, because they both have x3 in common, and see what we can do. So if we just bring that over, so we have x1 is equal to, and I'll divide by 2 to make it easier, so 3 minus x3. x2 will be 5. Yeah, 5 minus 3x2, and then we have x4 equaling 4. Okay, so this right here is called the general solution. Or more particular, if you have taken differential equations, this is called a particular solution. Okay. All right, so what we could do now is, well, what if we pick a couple things? Okay. Now, what I mean by that is, well, let's see. Yeah, we could do that. So we have something called independent variables and dependent variables. Okay, so just like going back to a line, x is always called the independent variable because I could plug anything I want here and then it affects y, when hence the reason y is called the dependent variable. So if I go over here, the same thing applies in this case. Well, since they both depend on x3, therefore x3 is called the independent variable. Okay? And our dependent variables will be x1 and x2 because they depend on the input of x3. Okay? So x4 is by itself because we have a solution, so it's not one or the other. It's just that kind of situations. Okay? But what if I want an actual question, right? So here's our general solution, and a particular solution means if I want a actual answer for x1, x2, x3, and x4, I just pick a number. So I'm going to pick x3 to be, let's say, 1. So now I just plug it in. So 3 minus 1 is 2, and 5 minus 3 is 2. So this will be our particular solution if x3 is equal to 1. And this will be our general solution in all cases. So now we can figure out if it's an independent variable or a dependent variable based off our solution set. And that'll get more importantly when we get to more complicated examples. Okay? So let's try another one out with more variables involved. So let's solve for the system and state which of the independent and dependent variables. Okay? So let's see. So it's already in row reduced form. Check, right? We have the first non-zero entries as the rows. Okay, so now let's write down what we have. So we have x1, x2, x3, x4. This is the answers, these are b's, and then x5. So we have 5 different variables we're going to be dealing with. So we have x1 plus 2x4 is equal to 3. Okay, we have x3 minus 9x4 is equal to negative 4. And then we have x5 is equal to 12, kind of similar to what we had above. Right? Okay. All right, so again, notice these equations both have x4 in common. So I'm just going to solve for 1 and 3. And we have this one here. Okay. So therefore, our independent variables we only have one, will be x4. And our dependent variables will be x1 and x3. And there we go. All right, so now what can we do with that, right? So when it comes to solving for a system, there are multiple situations we can have. We have one solution, infinite many solutions, and no solution, right? So when we have the case of an actual solution, we have, variables. This is considered infinite many solutions whenever we have this situation or this situation. Basically, we have dependent variables. Now, what does it mean to have no solution? Okay. That's where this comes into play. So a little different one. So no solution, or something called inconsistent system, it's a fancy word for just saying no solution, basically happens when we have this at the bottom. Now remembering there's a line here. So we have x1, x2, x3, and the b's. Okay. So what this is saying is we have an arbitrary, so this is saying 0 is equal to 1, which we know that's not possible. It doesn't make any sense, right? So again, it kind of goes back to like you're solving for a system using elimination method, and all of the variables cancel out. So you get 0 equals some arbitrary value like 5. Well, that means we have no solution. Same thing applies here, is whenever we have a row of complete zeros and it equals a value itself, this is considered no solution. Interesting aspect there. Okay. So now let's go on to our next definition. So let B be an n by n matrix. There is a unique n by n matrix C such that C is in reduced form and C is row equivalent to B. And again, this goes back to what we've been talking about before, right? This kind of makes sense. I have some matrix, and if I can row reduce it to I guess I just says 2 by 2. Those two are equivalent. Something we've been talking about already, but it's just another arbitrary. Now we're getting to more elaborate definition-wise and stuff like that. Okay, so now let's go into how do we solve a more complicated one, right? So it goes back to itself. So solving for a system of equations using the Gauss-Jordan elimination. So the Gauss-Jordan elimination is a fancy word for saying everything we've been doing. All we're going to do is solve the system using the 3 different rules for matrices, which is basically the same thing we've been doing anyways. Nothing's really changed. So in other words, our goal will be this, where these are going to be the answer choices themselves. But the problem is now we can have either one particular solution, infinite many solutions, or no solution now, not just an actual value itself. Okay. So again, nothing's really changed, so let's just do a practice problem here. Okay, so first convert this to its augmented matrix. Alright, so I have a couple options because I already have a 1 in these places. Okay, so maybe I want to move stuff around. Okay, so what I'm going to do, let's see what we can do. I'm going to we have the 2 here too, so let's get rid of this 1 here. So looks like I could just add, so I'm going to add row 2 plus row 3. And I'm going to put the answer in row 2. So I'm going to keep the row 3 the same. So if I add straight down, so this gives me 0, this gives me 14, 0, and then 14. And look at that, oh, that's kind of nice. Looks like we have already 1 done. So all I have to do is divide by 14 to row 2, and we have our first one down. got the middle done. Check. So now we got to worry about the other two. All right, so in that case, let's see, what can we do now? So why don't we make this a 0? So I'm going to multiply this by 2 and then add it. So multiply 2 times row 3 plus row 1. And I'll keep, so the second row is going to be the same. And the result, I'll put it in the bottom portion. So if I multiply this by 2, it'd be negative 2, 32, 4, and 32. And if I add it, oh, would you look at that? That also is pretty much done. So I'm just going to divide row 3 by 1 over 35, and that also now gives me the middle one. Well, this is interesting, right? Okay. Well, we'll just leave that for now. All right, so now that we have one complete row, let's get a 0 here. So I'm going to multiply 3 times row 2 and then subtract it to row 1. Or actually, let me just do the opposite. So row 1 minus 3 times row 2. Okay. So 2 minus 0, 0. 3 minus negative 3. Oh, sorry, this is a 2. My mistake. 0. Negative 4 minus 0, still negative 4. And then, so we got to be careful, right? This is a negative 3, so 3 minus 3 is 0. Okay. All right, so I can make this now 1 by, again, divided by 1/2, or 1. Okay, so we're almost done. We almost got our goal. So all I'm going to do now, I just need this to be a 0, which is pretty easy. I'm just going to now subtract row 2 minus row 3. And keep everything else the same. So that's minus that, 0, that minus that, 0, that minus that, 0, that minus that, 0. Oh, that's interesting. Okay, a whole row of zeros, which is okay, right? Because as long as it doesn't actually equal a number, we don't have no solution. So this is considered, we do actually have a solution in this case. And this is a 1. Okay, now that we row reduced it, right? We have 1, 1, and that's it. Let's see what we have. And remember, this was x1, x2, and x3, and these are b's. So this is saying 1x1 minus 2x3 equals 0. This is saying x2 is equal to 1. Okay. So if I solve for x1, we have these as our general solution. Okay. So in this case, we have infinitely many solutions. With our general solutions being that. Okay. Now again, if they ask for a particular solution, we just write them down. So x2 is always 1, and we get to pick. Let's say x3 we want it to be 2. So in that case, if x3 is 2, that means x1 is going to be 4. Right? And again, so we can write everything down. So our dependent variables would be x1, our independent variables would be x3. So now we can write anything down. But the whole process is, as long as if we don't get an actual answer or we get a situation like this, we'll always have infinitely many solutions on top of that. All right, so let's try one more. Okay. All right, so now we have 4 variables. So we already have an answer, which is nice. Okay, so now we just have to row reduce it. Now remember, it's not completely row reduced. We do have the numbers in front and the going down the diagonal with a bunch of zeros, but we have this being a problem, that being a problem, and those being problems. So those are the ones we gotta fix. Okay. All right. So let's first take this to 0. So to do so, I need to have the same number, so I'm going to multiply 2 times row 2 and then subtract it to row 1. So I'll do row 1 minus 2 times row 2. Okay. And then just for my sake, when I multiply, this will now be 4, 2, negative 6, negative 6, when I multiply by just 2. And now I'm going to put the answer in row 1. Okay. All right, so negative 1 minus 0, still negative 1. 4 minus 4, which is 0. Negative 3 minus 2 is negative 5. 4, and it's a negative, so both of these are negative, so 4 plus 6 is 10, and then 6 plus 6 is going to be 12. Okay. All right, so good. We're good. So now we got to figure out this one. Now I'm not going to do this one because remember, our pivot point was here, here, and there. Those are my only pivot points, not this one. Okay. So now, and it wasn't, we can't, so our goal was to do it, but we technically can't because if I try to get rid of this one, I'm going to get a number back over here, which is what I don't want. So the only thing I can do is get rid of these ones using my pivot point here. Okay. All right, so we'll just do this step by step. So that means I'm just going to multiply this by 3 and just add it to row 2. So row 2 plus row 3. And if you want, you could do them both at the same time, right? It's not that difficult. This one would be multiplied by 10 and subtracted, but we'll do it step by step. Oh yeah, we're doing this one first. Okay, all right. So we're just gonna, I have to multiply this by 3, sorry. So this can be 3 and then 6. Right, this plus this is 0, this plus this is still 2, this plus this is still 1, this plus this now is 0, and this plus this is now a 3. Okay, and then we just do it one more time with the 10. So I'm going to now do row 1 minus 10 times row 3. So this can be 10 and 20. So this plus this, oh sorry, minus, well, doesn't matter, it's still 0. $10 minus 10, 0. 12 minus 20 is going to be negative 8. And now it's in row reduced form. Well, almost, right? All I have to do now is divide by 2 and multiply this. So I'm going to multiply negative 1 by row 1 and then times it by 1/2 to row 2 to get my fully row echelon form. So divided by 2 gives you the 1. This is 1/2, 0, and 3/2. On top, it just changes the signs. Okay, and again, just remembering what our variables were. So this is saying is x1 plus 5x3 is equal to 8. x2 plus 1/2 x3 is equal to 3/2, and the one we already knew from the very beginning. Okay. And again, notice they have something in common. So we're going to solve for x1, x2 using x3. So our general solution we have infinitely many solutions, and a lot of the time it's going to be a lot of this, unfortunately, which kind of makes sense, right? There's infinite many solutions because all of these lines cross at infinite many times because these planes are going infinite, right? And a lot of the times itself. Okay. And there we go.